Hello, this is Professor Hester, and we'll be continuing our discussion of CCNA networking today by looking at Layer 1, the physical layer. There's so much to say about the physical layer that I've divided this video up into 3 parts. This is part 1, where we will talk about how to measure data movement throughout a network and look at copper cabling. First, let's review what the physical layer's job is. And that's to take data that it receives from layer 2 and translate it in the bits into signals. It's going to then put those signals on the media, which is the physical medium for transmitting the signals. And the most common type of media is copper. And copper wiring uses electrical pulses and is often found in smaller networks inside a building, such as LANs, which are local area networks. Another common type of media is fiber optics. Fiber optics have glass fibers that send light pulses through the fiber. It's great for sending data over long distances, and it can manage high capacity. So you'll find fiber optics in internet backbones, or between buildings, or across the city, or even between continents. And finally, wireless media is the media that we can't see because we are going to modulate electromagnetic waves through the air. This is the type of network that you use when you connect your laptop to an access point or a wireless router. So to compare the different types of media and how we configure them, we want to be able to measure data movement. So first, when we talk about speed, we're talking about moving bits per second, or BPS. And the most commonly discussed measurement is bandwidth. Bandwidth is the theoretical capacity, meaning this is the maximum amount of data that we could move through the network at any given time. But bandwidth is rarely achieved. Throughput is what we actually see. That's the amount of data that gets moved. So bandwidth may be what your ISP sells you. Throughput is what you actually get. And if you want to see what the throughput is in your network, you can use a site like speedtest.net to measure it. Similar to throughput is goodput, and this is throughput without the overhead. So when we move data through a network, we have overhead that manages the data, manages the connections, and so forth. So not everything getting moved is our actual data. Goodput would be the actual data that is moved through the network. And then related to speed is going to be latency, which is the time it takes to get to a destination, or the delay. So the overall time from the source to the destination is latency. And this becomes really critical in real-time networks such as voice and video, where we may be streaming. But the thing about latency is it's going to be limited by our slowest link. So if you took 2 high-speed networks and you connected them with a dial-up line in the middle, that dial-up line would be what would be slowing down your network, because you can't move data faster than the slowest link. And the picture on the right-hand side is an old-fashioned rotary phone connected to one of the early modems that you might have had in your home if you were one of the early adopters to bring a modem in years ago. All right, so let's look at copper cabling. This is the most common type of network cable that you will find. And on the right-hand side, you can see 2 ends of what we call a patch cable. So a patch cable is going to be used to connect 2 devices. For example, you could connect a desktop computer to a port in the wall using a patch cable. Copper cables have internally 4 pair of wires. And the little plastic ends on the patch cable are called RJ45 connectors. Copper cable can go anywhere from 10 megabits per second to 10 gigabits per second. But in reality, 10 megabits would be an old legacy network. You're more likely to find speeds between 100 megabits per second with fast Ethernet up to 1 gigabit per second. You can get speeds like 10 gigabits per second and even 40 in some cases with your higher level networks in data centers using the higher end cables with the newer protocols. One characteristic of copper cable is it's limited by the physics, so that once a cable gets to 100 meters long, it starts losing some of the data. The data drops off through a process called attenuation. So guidelines say we should not run cables more than 100 meters. And finally, the outside plastic jacket around the wires is usually a flexible PVC jacket. However, if you need to run cable in places like air conditioning vents or up in ceilings or places where you could have some type of flammable situations, you may need plenum rated cable. And with plenum rated cable, the outer jacket is less flammable and less toxic if it does catch on fire. However, this is a more expensive cable and it's less flexible to work with. We usually don't use plenum rated cable unless we really need it. One issue we have with copper cabling is signal interference. Electromagnetic interference, or EMI, is when our cable receives an outside signal. So we could have a cable next to a fluorescent light or some other type of electronic equipment where your cable is going to be picking up an outside signal. In the diagram on the right, the first picture shows the pure digital signal that we want to send. The second picture shows the interference in the area that we are also going to read. And the third picture shows what happens if we combine the pure signal with the interference. It looks very similar to the pure signal. However, there is a little variation, which we can see in picture number 4. There is one bit that actually gets changed from a 0 to a 1 because in that time slot, there's so much interference that it looks like we're trying to send data. So what this interference is essentially caused is for us to have our data be corrupted, and the data that arrives at the destination is not going to be the data we intended to send. So what can we do about this? One solution is to use shielded twisted pair cable, which we'll look at in a moment. And that shielding is going to protect our cable from the interference. Another type of interference is called crosstalk, and that's when signals cross from one wire to the other. So with 8 wires inside our cable, each one of them is sending or receiving data simultaneously, and sometimes that signal can bleed over from one wire to the other. A mitigation for crosstalk is to twist each pair of wires with different number of twists inside the cable bundle. And let's take a look at what that looks like. So unshielded twisted pair is our most common type of copper cable. You can see in the picture on the right that we have 4 pairs of twisted wires. Each of those pairs is twisted at a different rate, and this minimizes our crosstalk. You can also see a plastic core in the center. That's because this is a Cat6 cable, and Cat6 cable has some additional features to help it get faster speeds. Some of the time we need a shielded twisted pair, as we just discussed, to protect our cable from outside interference of EMI. The bottom picture shows a Cat6 cable that has a foil wrapper around the bundle of 4 wires, and that foil wrapper is what makes it a shielded twisted pair cable. This type of cable is more expensive than unshielded twisted pair, more difficult to install, so we're not going to use it unless we really have a need for it. By and large, unshielded twisted pair, or UTP, is what you are usually going to see in a network. The final type of cable I want to discuss is a coaxial cable. And this is your old-fashioned cable TV cable that you might have plugged in between your TV and your cable outlet on your wall. The ends screw in to the back of the device that you're connecting to, and it has a thick black cable. Today in networking, we don't see coaxial cables very often unless you have a cable modem in your house, but throughout the network, you generally won't see coaxial cables. All right, so we were just talking about how some of those cables were Cat6 cables. A little while ago, we talked about various speeds of copper cables, and let's now look at the different standards. The standards that you primarily want to be concerned about are Cat5 through Cat6A. The Cat5 standard is a legacy standard that's been replaced by Cat5e for enhanced. But our original Cat5 standard could only handle speeds of 100 megabits per second. And that's the cable that's on the right-hand side, the upper right-hand side of the screen. Cat5e replaced Cat5, and with Cat5e, we got much faster speeds of 1 gigabit per second, so it was a great improvement. Later on, Cat6 was developed, and a Cat6 cable can also get us 1 gigabit per second, but in some short distances, we might be able to get up to 10 gigabits per second. Then Cat6A for augmented was developed. That reliably gets us 10 gigabits per second. And then as we've continued on, developed faster standards, we have Cat7 and Cat8. And Cat8 can get up to 40 gigabits per second in a data center, but those are probably not going to be cables that you're going to run through the primary area of your network. If you want to learn more about Cat5 versus Cat6 cabling, you can go to electronicshub.org, and they have a great discussion about this. But for your CCNA exam, focus on Cat5 through Cat6A. All right, so looking at these little wires, how are we going to connect them? Let's discuss Ethernet wiring and wiring standards. So with copper cabling, we have two primary standards, T568A and T568B. With these two standards, they indicate which colored wire is connected to which pin number. And these standards have the same layout for the blue and the brown wires, but the orange and the green are swapped. And it's not really important whether you pick A or B, just that you are consistent throughout your building when you wire your network. The picture on the right shows this wiring standard of T568B and how it would appear in a straight-through cable. A straight-through cable is one where we use the same layout on both ends of the cable. So the left-hand side is going to match the layout on the right-hand side. And most of your Ethernet cables are going to be straight-through cables. A crossover cable is a legacy type of cable where we're going to swap the pins for the different pairs of the wires. So on the left-hand side, the wires that were connected to pins 1 and 3 are swapped on the right-hand side. And the reason you would use a crossover cable is because you are connecting two like devices, such as two PCs or two switches to each other. And since half of those wires were set up as transmission and half were set up to receive, they needed to be swapped so at the other end we would not have collisions and conflicts. However, these crossover cables are unnecessary with modern equipment. Modern equipment has auto sensing built into it so that if you do connect two switches with a straight-through cable, software is going to manage it internally and do the crossover for you. So it's no longer necessary to purchase special crossover cables. However, you do still see this concept on certification exams. The final type of cable I want to discuss is a rollover or console cable. This is the type of cable that you will use in a data center to connect your laptop to a router or a switch. And with a rollover cable, what you'll see is the wiring on the left-hand side is swapped with the right-hand side so that the opposite pin alignments are set up. So what was in pin 1 becomes 8, 2 becomes 7, and so forth. You're not going to use a console cable to pass data between devices. You're just going to use it to connect your laptop to the device so you can do some configuration or management. Now the cable that's pictured at the bottom of the screen, the light blue cable, is a standard console cable that was used for many years, and it's a serial cable. However, the connection at the bottom, that thick connection, has a place for 9 wires, and it's a DB9 serial port. However, most laptops and desktop computers no longer have a serial port. So if you're using this type of a cable, you need to have an adapter to convert that serial port to a USB port. Newer switches and routers now have USB ports on them instead of the serial ports or in addition to the serial ports. And so we can use a newer type of console cable that connects USB to USB. Then we don't need the adapters. But you'll still find a lot of equipment out there that requires the use of one of these serial console cables. And again, this is used for out-of-band management, where we are physically in the data center connecting our laptop to the equipment to manage it.